Так, hello guys, how's it going?
Good.
Good. How was your exercises?
Yes, come up. Now. Okay, he's reading. Yeah, wait here. Привет.
Okay. Are you ready?
Alright, sorry about that.
Okay, hello guys, no problem. Okay, so how was your exercises? Are they okay?
No, we did not get to the matrix. We were still doing the graphs. It took the whole week we've been doing graphs. We just didn't get to the matrix. Sorry about that.
Okay, so you will come to it. I hope.
Yeah, it's just that's how long it takes them to understand things.
Okay, just don't forget to do it. Okay. Okay, so today's name is number 17, and the theme is dimensions. We'll talk about what about it. We talk about it from time to time. You know, about 2 dimensions, 3 dimensions, 4 dimensions, space-time, right? Something about it. But now we have to understand at least a little more about what are those things that are called dimensions. Okay, just talk a little about it. But first, let's take a look at one interesting thing. Like we have 2 coordinate axes, right? Y and x, for example, right? And we have certain like vector like A, right? And remember what we were going when we're taking coordinates of this vector or components. We do a so-called projection, right? We pass perpendicular, right? Remember? Pass from the end of the vector to the axis x and then to the axis y, right? And those, when we do it, this passing these perpendiculars, these are called components or coordinates. Sometimes they say coordinates of the vector A, right? But let's look in reality what we do actually there. Okay, we were talking about that vector A by itself is invariant, right? Invariant means that it's like sort of an object, so it does not actually feel anything what we're doing around. Like we are putting our coordinate axis, we look at it, we pass this like projection lines, right? These perpendiculars, everything, and looks like it should not touch this vector A. But in reality, it is never the fact. In reality, when you do anything around certain object, we should touch it somehow. Even if we look at it, it means that the photons from the sun or from your lamp goes to your object, right? and is reflected from the object and comes to your eye, or something else. If you talk like mathematically, what we are doing when we are passing, where we project this point like point A, right? Project point A to the axis x. What do we actually do? We need to pass this line, right, first. But to pass this line, we should to put some points there. We have point A, right? And if we want to start from point A, we should at least touch this point. We should put our pencil here, right, and then pass something like this.
Yeah.
When we put the pencil here, right, actually what we do, there was already point A, and now we start from this and starting moving this way with our pencil. What we do, actually in this point A, first of all, we double this point and we get point A prime. They're very close, right? At the first moment they maybe could totally coincide, but still, one point belongs to the object, another point belongs to us, to our pencil that we touched it. In reality, it's always like this. There is always some pencil, photon or whatever, that touch the real object. And what happens when you touch it? Okay, the point, there are 2 points in one. If you, like 1 or 2 points, There's actually a paradox. Remember this Zeno paradox of arrow?
Paradox?
Zeno. Remember?
Zeta?
Zeno paradox, yeah. Or Zenon.
Yeah.
So this paradox, remember, there the arrow. To move, it should be in two places at the same time. But actually it's always in one. So this is a paradox. Here we have the same thing. Because we are moving with our projection, right? We actually get 2 points and they should be in one. So this is, again, we return to this old Zeno paradox. So we're doubling the points. One of the points, A, belongs to the object, another belongs to us, and us are called subject. So something that is connected to us, to observer, to the person who actually doing this so-called experiment or whatever, measurement. So what happens then if it's doubled? One is an object point, another is subject point, right? It doubles. So we are passing this line here. So the point is moving this way, right?
Yeah.
Down. What will happen with this point? Remember, these points at the beginning, they were one. And then they just separated from each other. What happens? Just take a look. This point A prime, it is actually a small frame of reference. Because A belongs to the object and A prime is a small point of reference. Somewhere here, very close to the point of the start, right? So remember, when we move the frame of reference, what happens with this, with the point itself?
I don't really understand the question, Digga. Me neither.
Okay, for example, if you have the whole axis X, right, and you start moving it down, what will be looks like with the point A?
Well, point
Would it move? Huh?
The point A stays where it is.
No, stays, yes, but from the point of view and frame of reference.
I don't get it.
Oh, we can return to the car. When you're moving into the car, we're moving to the car. What happens with the objects around?
They go the opposite way.
They go in opposite ways. That's only the simple question, right? So this point looks like it goes up. This point goes down. This point goes up.
Oh yeah. Yeah.
So this is like a simple thing. It seems simple. It's not simple. It's a paradox actually, because it's totally connected with the Zenon paradox. But it is exactly what we have in reality. When you touch something, right? This what you touched started moving one direction, and your finger feels the pressure, so it wants to go opposite direction. It's called reaction of the things. So that what happens, just for you to understand that this is not that simple as it may seems to be. Mathematics is very, very strong idealization of reality, and all these things happening, even if you're talking like on mathematical level, but in reality is even harder to understand. So this is about projection. Now let's talk what happens.
You're gonna have to wait.
What happens later? We have the thing that we call dimensions. Remember that we were talking that the basis vectors are so-called linear independent. So it means that they're just, you may say that they are just independent. Each vector directed to the coordinate axis, right? They are independent if they are perpendicular to each other. Remember that? We were talking about this.
Yeah.
It's called linear independence mathematically, but in simple we say that they're independent. So whatever you do, you cannot get this vector by summarizing these two. You cannot get this vector of summarizing of these two. And you cannot get this vector from summarizing or whatever, doing so-called linear combinations of this vector. So they are called independent, or more mathematically linear independent, right? So how it looks like, and they are called these directions are called dimensions. So how it looks like in the simplest way. Let's get some axis x, right? And we have some point. We have some point, right? When it moves, or in other way, the point is doubled, right? There are 2 points. Like, for example, one point moved from this point. This point moved relatively to this. This is actually called relativity. So one point goes this way, the other point, from this point of view, goes this opposite way. It depends upon the point of view. You're standing on this point or standing on this point. So they're moving separately, but look at this. If we move here, we have this point, right? If we move here, we have this point, right?
Yes.
If the points are really close, you see that the central point from the starting point, like point A, right? Here it is, point A. It has only 2 neighbors, 2 closest neighbors, this and this. One on the left, like maybe A minus, one on the A plus. On the left and on the right.
Yep.
Only two neighbors, right? Okay, on the line. Let's go from the line. Let's go to the plane. We have points on the left and the right, and also points up and down, right? So we have neighbors here, right?
Yep, you would.
So on the plane, we have neighbors, more neighbors than on the line. And this is exactly what is connected with the understanding what dimension is. Dimension is about closest neighbors, or the links that any point have with other points. If you have only two connections, right? 2 neighbors, left and right, this is one-dimensional space, right? If you have at least 4, right? You have 2-dimensional space. It's a plane. If you have more, like here, right? You have left, right, up, down, and here on the Z, here and here, right? You have points here and here. So 2 more. So if you have 1, 2, 3, 4, 6 neighbors, 6 closest neighbors. This is called 3 dimensions. And now let's think about this thing. Remember again, return to this Zenon paradox, right? The arrow is moving, or a point is moving this way, right? And according to the paradox, it can be in 2 places at the same time, right? But it cannot, because it's only in 1 place. So, and this is paradox. It cannot be in 2 places, should be in 1 place, but anyway, to make movement, you have to be in the 2 places. But why just in 2 places? Just think about it. Because we are talking, we're looking around and we see that arrow or whatever just moving in 1 direction, some 1 line, right? Then we talk about that there are 2 points, okay?
I don't get the question.
Okay, the question is, you have 2 points, right? In Zenon paradox. Remember?
Yeah.
2 points. But why 2? Why it cannot be like 4 or 6? Because we presume that the arrow is moving just in 1 line. So it's 1-dimensional movement, right?
Yeah, but
Yeah. What I'm talking, that we presume it, right? But it's not proven. It looks like that, but who knows? Why it should be two?
Isn't it like this because two dots make a line?
Two dots not. That's all. It's all about axioms, right? But axioms are axioms. Axioms are taken from where? It's good to live with the axioms, right? Difficult to live without axioms, and that's the whole point. But the reality is not about axioms. It's about something else. There are laws of physics and everything, but laws are not like absolute. Like the laws that we have now, maybe not the law tomorrow, because we'll discover another law. It's much more. Usually, the next law gives nature much more freedom than before. So it's law, but not that strict that it used to be before.
Oh.
Yeah, but anyway, so what I'm talking here, yes, one dimension. And as Katya said, right? Why not? Can be maybe more, right? Why not?
Yeah,
We don't know. We presume that it's moving like in one line. Yes, it looks like that arrow goes by line, right? Like maybe photons from our flashlight goes straight line, right? Looks like. But it's not always straight line one thing. Like even photons, they go around sun. You know, it curves, the line is curved. Photons are actually pulled by gravitation pull to the sun, and it's measured. So even that not correct, but maybe the photon moving something like in different way. Maybe it does not go to one point, maybe it goes to many points whatsoever. And actually the reality is pretty much like this. Actually it happens so that in quantum mechanics, like quantum theory, right? Each point in space-time, so some quantum, some material point, right? So some point that you can touch or whatever you can do, not idealization of it.
Yeah.
Each point actually can be not in one place, but in many places. Actually, it can be in infinite amount of places. Infinite.
Yeah, that makes sense.
It makes sense. And also, what the result of it, that actually we are dealing not with even four-dimensional space-time, right? Like we used to, but infinite dimensional, infinite D, and again space-time. There are many space dimensions and many time dimensions. I'm not going about it, just for you for your fantasy, you know, something like this. So we are dealing, in reality, we're dealing with infinite amount of dimensions. So just think about it. I will talk about it a little later, and now let's make some example of multiple dimensions, more than three. It's pretty easy to talk about three dimensions, right? Remember, we start from projections, right? From projections. So, like vector if projected, right, it gives that kind of line, projected right here, right? For example. So you understand what projection means. And now let's talk about some real figure, like in our space times, right? First of all, let's talk about cube. Cube, pretty simple geometrical figure, right? And the cube can be multidimensional. And when you go about cube in many dimensions, they usually write like n cube. Like n is the number of dimensions.
Yeah.
So let's start from 0 cube. What do you think? What can this be?
0. It can't be anything. It'd just be nothing.
Yeah, nothing. Actually, nothing in geometry means point. So this is 0 cube, mathematical point. Infinitely small, you know, and no dimensions. Not at all. So no neighbors. So just one, single. No links to anything else. 0 dimensions. Now, 1 cube. What do you think? What can this be?
1. Well, it'll just be a line. That's it.
A line, yes, but remember, cube is has boundaries, right? Line has no boundaries, left and right. It's minus.
Segment.
Huh?
A segment.
Segment, yeah, interval, right? Well, I don't know what's the term. Interval?
Segment.
Segment. Okay. Yes, right. So we have 2 points, right? These are sides of the cube, and this is one-dimensional cube. Yes, you're correct. So segment. Now 2 cube. That should be easy.
A line. It's still a line. Oh no, that's a segment.
Segment is 1 cube. Have 2 sides, right? Also, how they call faces? The sides of the cube.
Yeah.
Huh?
Yes, faces.
Faces. So 2 faces, right? Left face and right face, right? Here no faces at all. Left and right. Left.
It's a
Right.
big plane.
What about 2 cube?
A plane has no boundaries.
Yeah, the plane. Yeah, the line itself has no boundaries. So these are boundaries. This is 1 cube. This is.
Like,
What about 2 cube? You know what is 1 cube, 0 cube, and 3 cube, right? 3 cube, it's easy, right?
yeah.
What is it? Yeah. What is it?
Okay, we know 3 cube.
It has length, width, and height.
So what is it?
A square.
Length, width, and height?
Oh, it's okay. It's a square. It's a square. Look, it's a
Right, this is square, exactly.
Good job, Katya.
And we have got left, right, up and down, right? These are faces, right? We have, this is 2 cube. And look also here, 0 dimensions, no neighbors, right? Here, 1 dimension. There are two neighbor cubes on the right, and on the left. You see?
Yeah.
Here, how many cubes connects to this cube? The neighbors. So here, right? Here, here, and here, right? So how many? 1, 2, 3. Here is 4.
8.
Oh, here.
Oh.
Okay, here is 4.
How many?
And here,
What?
how many here? For 3
Four.
cube?
Yeah. Huh?
How many neighbors to this?
Height. What is
How many faces?
Faces?
Oh, 6.
Yes, faces is a boundary which connects to the other cube, right? So,
How many? Six.
6. Oh, did a 6.
yeah, like a dice, right? How many dice? You know dice?
Yeah.
How many sides, faces?
6.
So 6, right? 6. Here is 4. Here is 2. 2, 4, 6, right? Now let's talk about 4 cube.
Oh, it have 8 faces. Would have like 8. That's a hypercube.
Yeah,
It's a
oh.
hypercube.
Oh, so you know Hypercube?
Yeah.
Okay, good. And you know how it looks like?
No. No one knows how it looks like.
No? You cannot see it per se, right? But you can see it in projection to our eyes. Our eyes are actually it's a surface, like so. It's 2D, two-dimensional thing, each eye, right? So we have a projection to the plane, to the two-dimensional surface. So we can talk only about these projections, right? So and the hypercube looks like this. So you have. It should have, you said correct, it should have 8 faces, right?
Yeah.
It's easy to take from here, right? 2 plus 2 plus 8 faces. And look at these faces. Here, you see, here, each face is a point, right? And point is 0 dimension. You see? For 1 cube, each point is 0 dimension, point. Each face is 0 dimensional. For the 2 cube, each face is how many dimensions? Each face, this face, this, huh? 1. 1, right. So here is 1. Here each face is how many dimensions?
2 dimensions.
2 dimensions. So here each face has how many dimensions?
2.
Here is
No,
2.
it have 3, right?
3. Each face.
3
Each
dimensions.
face 3D. And because they are all like squares, I saw 3D face, what is it? 3D cube.
Yeah. Each cube is its face?
Yeah, the cube is a face, the side of the 4 of the hypercube, right? 4 cube or hypercube. So the 3D cube is a face, and there are 8 of them, right? There are 8 of them. So how can you imagine such thing? How you can?
I think I don't get it.
Okay. I just will paint it, right, somehow like
Yeah,
this.
I'm not joking. That's actually how I thought it. Oh, never mind. It's not what I thought it would be.
It's like this. I don't know. I tried to do it as accurate as I can, but so this is cube inside. You see the big cube. There's a big cube. Inside is a smaller cube, and this cube is connected with these lines. Here, here, and here.
They're actually planes, I think.
It's just projection. But each this thing, like for example, this, right? 1, 2, 3, 4 here. Each this thing is a cube. It's just it is deformed because we project it on two-dimensional plane. All these things are cubes. Upper, lower, left, right, front, back. All of them are actually cubes. And if you unfold it, how can you unfold it? Like for example, how can you unfold this? Imagine this is the wires, right? So it will be like this, 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 right?
Yeah.
Just break it here and unfold. It will be like this, right? Now break this like in one place and unfold. What will happen? You will have these squares, right?
Yeah. Yeah.
1, 2, 3, 4, 5, 6, right? So
But
this
how is each a cube? Each of it is a cube for the hypercube.
and if you unfold this,
You see cubes.
you will see cubes, and there looks like that.
Isn't it impossible to unfold it though? No, this is just doing it right now. Oh yeah, now I see the cubes in there.
And this way, right? Cubes. So like a cross of cubes, like this.
Oh wow. What the heck? That's
Yeah.
cubes.
So this is unfolded hypercube into real cubes. Each thing is 3 cube, and how many of them? 1, 2, 1, 2, 3, 4. In the middle, 5, right? Oh, just 1. Jesus Christ. 1, 2, 3, 4, 5, 6, 7, 8.
7.
Yeah. You can try to picture it yourself. Just draw it somewhere in your place. You will just to find it out. Okay. So you see that even hypercube, this 4 cube, is a pretty complex thing. But it looks like, at least if you look at it, at least it looks similar to all this, right? If you do all these things. There's one way, interesting way, how you actually can create the cube of any dimensions. Or projection, of course, of its projection. So like two-dimensional picture of any dimensional cube. Pretty interesting way. And you may as well train yourself to do it. So what do? It's all going about projections. See, we talk about projections, dimension projections. So we have 0 cube, right? Here.
Yeah.
So let's put a projection to some other place. Here. For one point, another point. So, projection.
Yeah.
It's called actually, what's the term of this? That's a pretty interesting term. Jesus, I forgot. Orthographic. This method is called orthographic. So, or parallel projection. So you put parallel projection and you get immediately 1 cube, right? This is 1 cube. It was 0 cube, and by projection cube, right? Now we have 2 points, and we make 2 projections. Here and here, up, and you have
A square.
and how many dimensions? What cube is it? 2 cube, right? Now we have 4 points, right? And we make the same thing, four projections. This way, this way, this way, and this way. And we have
A cube.
3 cube, right? Now from 3 cube, how can we get 4 cube? The same thing. Now we have how many vertices, right, Antosh? Oh, how you call this?
Vertices.
Vertex?
An edge.
Vertices. Or vertex. Vertex is
Vertex, yeah.
Oh, that's an edge.
No.
This is a vertex.
Lines.
Yeah, that's what Dad is talking about.
No, I'm talking about points. No, I'm talking about points. Vortices, right?
Oh, okay. Yeah, vertices.
Vertices.
Vortices, right. So how many? 1, 2, 4, 8 vertices, right? So what do we do? Again, we do projections for each point. Okay, this way, this way, this way, this way, this way, and we have again, and we have after we make all these projections, right? We have the same cube, but projected here. Another cube projected here. So each vertex is projected to another vertex. Did you get it? So each of these get parallel projections like a shift. You might call it shift, or there's a how it is called, translation, right? Shift translation. So you just move it this way and you see this. This is a projection, actually, believe it or not, but this is a projection of Hypercube. Just play with it. It's very interesting. Try to maybe do projection in different directions, maybe something good. But if you look at it, and the Hypercube that I drew before, you will see that this cube is actually inside. It just made smaller and put inside the first cube. But the projection are just turned into inside this cube. If you look at it, you'll find out. So this is okay, and the same way, believe it or not, but the same way you can plot on your plane, on your on your whiteboard or whatever, your sheet of paper. You can plot the cube of any dimensions. Just maybe a little tricky, but you can do it. So there is a way how to do it. And the guys had lots of fun with this. They actually did it many times. So they are pretty interesting pictures, believe it or not, in this way. Now just a short thing about dimensions and our space. I talked about this in quantum mechanics, right? The quantum theory, actually, quantum theory dealing with actually multidimensional, actually almost infinite dimensional space, right? But there's an interesting thing, believe it or not, but you yourself, each of you, has in your organism some system which is almost infinitely dimensional. And I guess what can this be?
The brain?
Yeah, right, the brain, yes. If you look at the brain, especially so-called associative fields, associative or lobes, associative fields of the brain, these are the main parts of the brain which are making associations, and actually they allow you to think. This is your thinking fields. They are mostly here, in that part of the brain. So with these fields, and the brain, you know, it consists of neurons, right? Or nerve cells, neurons. And how many direct neighbors each neuron in the brain can have? What do you think?
Infinite?
Not infinite, no. There's difficult to say. We don't have infinite amount of cells in our organism, totally, right? So brain itself has about 86, I think, billion
No, it's about 24 trillion cells we have.
No, in the organism, right? But I'm talking about neurons in the brain.
Oh, neurons, yeah, about 80.
So it's finite, right? So it's a billions, but finite. So, but how many neighbors, direct neighbors, has each neuron? What do you think? Direct neighbors should be, it contacts, right? It contacts with other neurons directly. How many neurons each neuron, especially in these associative fields, actually connects? What do you think? How many?
I think 86 million, probably.
Not millions, but it's about 10,000. So it's pretty much amount. It's very close to infinity. It's not infinity, but very big thing.
I know.
And let's think about it. Actually, what does it mean? Okay, 10,000 may be infinite, like in quantum mechanics, there are infinite projections, right? Or infinite dimensions. So, what it means actually for the brain? Like everything which goes to the brain, like it goes like from your eye, right? There are neurons in your eye, but they are located on the surface, which is called, forgot how it is called, which takes.
Isn't the cornea?
No. Сетчатка, как она, то, что не помнишь, как сетчатка?
Cornea.
Cornea. Cornea. Okay, so you're right. So cornea, right? And it is two-dimensional. It's 2D, right? So neurons are located here, right? But when the signals goes to the brain, especially to associative fields, right? They goes to the realm of 10,000 of connections, so 10,000 dimensions.
Oh man.
And what can this be?
Difficult to feel.
Like imagine that you have cube that we talk about, right? Like 3D cube, right? We can turn it and look from different sides. Maybe it's not differently cube, but something, right? Maybe some pictures on the sides, right, on the faces, something like this. So to understand what is it, we would rotate it before our eyes, right? To look what is it about, right? And how many faces we can see in the regular cube?
6.
6. That's it. So all rotation give you six faces, right?
Yeah.
But if you have something that is represented in the brain, 10,000 dimensions, so it is 10,000 faces. At least.
Imagine that.
So when you see something, right, it gives you, it forms some image in your brain, but it's just small part of the whole image, which is 10,000 dimensional. And as a result, if you see, like, for example, you see cat like this, right? One cat. Another cat, maybe like this, sitting cat. Another cat, maybe falling cat.
A what?
Falling.
Home care?
Falling cat, like this cat, right? All kinds of cats. Cats after big dive, right? In the water, right? All the hair like this, right? And this is cat again, right? And all the hair like this, and wet. Lots of different cats, lots of different brides of cats, all that sort of things, right? And you see all these cats in your life, and it forms a picture in your brain, which is called cat in general.
Cat in general.
General cat. Oh, yeah. Absolute cat.
Cat general.
Cat general, right. Absolute cat, right? Or something like this. And interesting enough that if this picture is formed, right, in your brain, you can turn it in a certain way in your brain, because brain can turn your images. Even they are 10 dimensions, they can turn it in any position, right? You can find out that there are certain types of cats which you never seen. That's how your fantasy works. Like, imagine a cat. You can imagine a cat that you saw. You can imagine a cat that you never saw. It's your fantasy cat.
Yeah, because we can do what you can do. You can kind of like use all the types of cats to get into one cat.
I imagine
Maybe one darling cat, please.
Right.
imagine a slug with hair.
So now you at least may understand that by rotation, you know, and the other changes, by the way, other symmetries in your 10,000 dimensional brain, right? You can imagine lots of things that didn't exist, you never saw them or whatever. With the cats, with other things, like with maybe mathematical formulas, mathematical invariants that we're talking about, and lots of other stuff. So it's a very, very useful thing, multidimensional. Remember that even function, each function, right, it is a infinite dimensional vector, right? Remember? I told you.
Yeah.
So this is 2. Okay, and what else I want to say? Maybe just one phrase. Antosha, your papa knows, and you should know that you're entering the age of
Capitalism?
Capitalism?
Stop.
Neural networks.
Neural networks?
Neural networks. And these neural networks will be on quantum media or quantum computers. So quantum neural networks, this is our future, very close. When you go to university, you will be dealing with these things. They will be everywhere already at that moment. So, and those things are based on multi-dimensional, infinite dimensional quantum space-times. And they're very powerful. They're already powerful now. They will be even more powerful tomorrow. Okay, guys, any questions to this?
No.
No? Okay. So I have questions to you. Get a pen, a pencil.
Okay.
Okay, the first is construct 5D cube.
Construct what?
Projection. 5D. 5 cube. 5 cube. You have 4 cube, half cube, hypercube, right? Construct 5 cube.
Okay.
Second is suggest, think about what's the best picture with how to how to move these things to make the best picture. More beautiful, maybe.
Sorry, what is the question?
Suggest the best picture of the 5 cube. I've shown you how to do it, right? So you by projections, you can do it. Right now, just imagine how is the best to picture it, the best way. And the third question is, you wrote, right?
Yeah.
The third question is, what do you think? How can infinite dimensional, infinite cube, like infinite cube, how it may look like? What do you think? Just use your fantasy, just think about it. How may this cube look like?
Okay.
And if you don't know, if you just think about how hypercube can look like, what's the best picture to make this 5 cube, whatever, and then you may think about multi-dimensional, infinite dimensional cube. That's it.
Okay. This was interesting.
Okay, guys.
It really was interesting.
Okay. So
Okay, thank you.
see you next time.
Yeah, this was
Oh,
good.
can we see Bible?
You want bubble? Okay, just a sec. Okay, see you.